Welcome to Tier 1 design checks for suspended bridge design. The concept of Tier 1 through 3 design checks are varying levels of detail and already discussed in the previous text session. And this video is meant to go into more depth on how we can use this level of analysis for standard bridge design. Tier 1 assumes you are using standard drawings, and the design process is very linear. By this, I mean you set up your inputs based on bridge geometry and materials available, calculate a series of outputs from standard equations, and choose the closest standard design that works. As described in the previous section, this is not a bad thing, but in order to increase efficiency, further customization will be required, and therefore delving into the assumptions behind the prescribed equations will be required in Tier 2 and Tier 3 analyses. By the end of this video, you should be able to understand the Tier 1 design checks required for cable analysis specifically, be able to apply this process to all other design checks, create a flexible tool for design checks, and create PDF documentation of your design calculations. As an example, we can use the geometric profile and material of information available and used in cable analysis. We won't go into depth on layout and design because that is covered by Jay in previous lectures. But if you need a refresher, please go back and check out those videos. Now, as inputs, we need to define span, abutment height difference, distributed load, cable diameter, and cable ultimate breaking strength. From the mock review called deliverable, let's take the 65-meter span and 2-meter delta H bridge and assume distributed load is 1 kilonewtons per meter at its maximum case of dead load plus live load and soil pressure. And we'll also assume a deck width of 1.04 meters with wooden crossbeams. Remember, this means a minimum of 5 total cables. And finally, 1 1/8 inch cables with a 474 kilonewton breaking strength. You can find the unit weight for these cables in the Bridge Builder Manual in Table 3.1. Now we'll move on to the split screen view where I can show an example spreadsheet and the Bridge Builder Manual. That I used to create that spreadsheet. I'll assume you're familiar with these equations and the schematics from the previous lectures. I built this specific spreadsheet with 4 main tabs, excluding the example tab here. The loads and bridge geometry, bridge design, and loads and material properties. These are all fixed inputs, which I keep up front, while the cable analysis tab would represent the first of all of the design checks that you can begin to add to your spreadsheet. These fixed inputs are tabs that I use to change, and I'm constantly using within those design check tabs. Anything that I change in these first 3 tabs should be able to update in all subsequent tabs to perform design checks. Notice that I also use comments and notes that are relevant to that specific section. For example, as a sanity check, PV back should be greater than PV main. These notes and comments, such as note that the B2P design is based on the geometry created from the dead load sag, are relevant to each section, and they help me remember specific tidbits of feedback that I may pick up over time, or they help me remember small caveats from the design manual. In other tabs, I have links to resources as well as drop-down menus in order to decrease room for error. And for a quick insight into how this spreadsheet becomes flexible, I'll fill out a few of the squares. We can start with the dead load and live load sag, which is 6.1% of the span. We make sure to reference back to that input tab for loads and geometry. So let's quickly make sure that span is 65 meters. And for the horizontal tension, we'll use this equation here, the distributed load. We'll use with the total load reduced live load times the span squared divided by 8 the dead load plus live load sag. Remember to keep everything dynamic, and it will make your life easier in the future as you inevitably make changes to your bridge design and work through those various tiers of complication and customization. Now I'll fast forward through the rest of this process in the interest of time. Now that we have all of these subsequent calculations made, we'll use the Tier 1 standard design procedure of cable design based on the largest tension divided equally amongst all cables. This top square just takes the maximum tension experienced on the high side. As you can see, it's just the maximum of this section. Remembering our allowable strength design equation, the maximum tension multiplied by some safety factor must be less than the ultimate breaking strength of a cable times the number of cables. Following this concept here from the design manual. So here we can see the fixed safety factor, and we can set the max breaking strength multiplied by the number of cables and play with the number of cables. So that maximum breaking strength is going to come from one of our inputs tabs, the loads and materials, right here. And then our number of cables, let's say we start with 4. And for ease, something I like to use is called the demand capacity ratio. You could just take these two numbers multiplied by these two numbers and compare it with these two numbers multiplied, but I like to use the demand capacity ratio because it shows you how efficient your design is. Here, we just take the left side of the equation, factor of safety multiplied by the axial tension times divided by the ultimate breaking strength times the number of cables, and that should be less than or equal to 1. The closer you are, the more efficient your design is. So if we bump up to 5 cables, which is what is required for the minimum for wood crossbeams, our DCR goes down below 1, so we know that our design should work. We also could multiply these two numbers and compare that with these two, and we see that it is larger, so our design should work. Now, when you're going through this process, make sure to flex your sheet. Change some inputs around and see if you get a reasonable answer. Make sure it works with various bridge designs to accommodate future changes too, instead of just one design. Also, feel free to use a tool other than Excel, such as MathCAD. I just use Excel because it is what I am most familiar with. So for example, if I were to change this span to 90, like it was before, and go back into my example, I see that even with 5 cables, our DCR is greater than 1, so it wouldn't work. I can go down and look at the numbers here and see that our capacity is less than our demand, so the design wouldn't work. Finally, if you're using Excel and just submit a PDF, you must at least show your equations. So submit the spreadsheet or copy those equations into your PDF, because it's very difficult for the reviewers to find potential mistakes if these equations aren't available. When reporting design calculations with a PDF, many good examples have been uploaded in the Technical Resources section of Bridge EDU, in addition to any resources your team may already have. Here in the Technical Resources, one good example is the example suspended bridge calculations from B2P. Notice how schematics are used for context, showing the reviewer what part and aspect of the bridge you are referring to. Also, make sure your information in the calculation package is standalone. Don't refer to previous reports unless otherwise noted by reviewers. They must be able to find all information within this document. Finally, some of these resources may have more advanced calculations, so always use the review call guides and checklists in the Bridge Binder appendices. Before we move on, I want to show a free tool you can access by registering online at overleaf.com. Here I've uploaded a structural package template to the additional resources portion of the course. Sorry, I need to open that in another tab. Here's that LaTeX example file that you can upload into overleaf.com. And once you sign into overleaf.com, this is what it will look like. Now, using LaTeX through overleaf.com can be overwhelming. It is an extremely valuable skill to have to make well-formatted and professional engineering documents. Anything you can't do by just replacing and copying text is generally also accessible on Google for information. Also, feel free to reach out to me for help. Additionally, these documents can be worked on like Google Docs using the Share and Review tabs up here. As you see, this is a structural calculations package example, and what you need to do as you look through what the PDF rendering is. Here, you just find what you want to change here or copy and continue and go through this process. I promise you will get very familiar with it very quickly. Now, inevitably, customization will become part of your design process. And with this, you'll need to start dismantling some of the standard equations in order to make your bridge work. For example, starting to analyze individual cables instead of assuming they all pick up equal load. Now, while we work on creating an advanced design course, work with your design engineer in charge, as has been done in the past, in order to complete your design for Review Call 2. Now that you've watched this video, you should be able to understand the Tier 1 design checks required for cable analysis, apply this process to other design checks, create a flexible tool for design checks, and create PDF documentation of these design calculations. Thank you.